Today, we are going from lens cover to 3D scan using a RevoPoint Metro Y. Follow along to see how. We are going to be using the turntable included with the RevoPoint Metro Y Pro for this scan. It makes it super easy to capture scans and still monitor what the scanner is doing. We'll be mounting it on the tripod included with the scanner. Alright, so let's go take our first scan. This is a lens cover for a truck, and the biggest problem is that transparent objects do not work natively with laser-based 3D scanners. For that, we're going to need 3D scanning spray. As you can see here, without scanning spray, the scanner cannot pick up on any details within this object, which is why we need scanning spray. This is also needed for total black objects because it absorbs too much laser light. I am using RevoPoint 3D scanning spray, which is a no-clean spray that goes away in 2 to 6 hours. The main thing when applying scanning spray is not to layer it too much because that will destroy detail, and to be careful touching the part because that can cause imperfections. My first scan was going good, and I was just checking the data, making sure that everything was okay. It was on its second pass at 10 degrees, and I had the turntable set up to pivot at 10 degrees the first pass, 20 degrees the second pass, and on the second pass, it caused my tracking blocks to move, which caused tracking to fail and is very important to prevent trackers from moving. But it wasn't that big of a deal because I pretty much just started and I was okay with just redoing another one. You can see that all the trackers are offset and the tracking blocks have been moved. I broke the scan up into 4 separate scans. I did the first one at the top with the turntable mode. I did the second one on the bottom in handheld crosslines mode, and the third and fourth were single line mode to try to collect data on the holes in lens cover. I want to maintain a constant distance from the part and move slowly enough for the scanner to collect reliable data. Moving too quickly can cause tracking to fail. Moving too slowly or repeatedly scanning the same area can create excessive data without improving accuracy. The goal of this first scan is to capture the primary exterior surface and enough surrounding geometry to help align additional scans. It is important when you do additional scans to collect enough data that you can align them. If you don't, it's impossible to align the scans, and you'll have to redo the scan. One scan cannot capture every side of the lens. The scanner cannot see surfaces that are facing the table or blocked by the part itself, so I need to reposition the lens several times and capture additional angles. During these passes, I am focusing more closely on the rear edge, mounting locations, and areas that were hidden during the first scan. Certain parts do not matter, such as holes, because we can measure them later on. However, the lip of the lens cover and basic shape need to be scanned to allow for precision reverse engineering. It's important to understand that raw 3D scan data isn't ready for immediate printing. A 3D scan is simply a collection of data points. Attempting to print that data directly would result in a model that fails to function correctly. Instead, we must import that scan into CAD software, where it serves as a reference to rebuild a precise functional design. But now that we have all this scan data, we still need to process it. So let's head over to Revo Metro and melt our PC. I begin cleaning the raw data. This includes removing the table, scanning fixtures, floating fragments, and any other geometry that does not belong to the lens. I can also fill small gaps and reduce isolated noise, but this needs to be done carefully. Excessively smoothing can erase real features or change the shape of the original part. The objective is not to make the mesh look artificially perfect. The objective is to preserve the useful geometry while removing obvious scanning errors. After cleanup, we can align the scans. This produces a much more manageable digital reference than the individual raw scans. Now we have several individual scans, but they still are separate pieces of data. The next step is aligning them into one complete representation of the lens. The software may be able to automatically identify matching surfaces, but difficult geometry sometimes requires manual alignment. For manual alignment, I select matching points or recognizable features on each scan. A small alignment error can become a significant problem later, especially around mounting features or thin edges. Before exporting the scan, I inspect the final mesh for missing sections, obvious distortions, and alignment problems. I am checking whether the major curves are continuous, whether the perimeter was captured, and whether the mounting features contain enough information for the next stage. This does not mean the mesh is ready to manufacture. The scan still contains thousands of potentially millions of individual polygons. It is a reference data that will guide the CAD reconstruction, not the final engineered model. Reverse engineering is more than just 3D scanning something and calling it a day. This data is very helpful to make sure that your part is within tolerances and to base those ideas off of. But most of the modeling is still done in CAD programs. We now have a cleaned and refined digital scan of the lens cover. This file captures overall shape, curvature, perimeter, and mounting areas that we will need during the next phase. I will import the scan into CAD and begin rebuilding the lens cover. That is where we separate the intended design from scratches where distortion and other imperfections in the original part. At CAS Design Co., scanning is only one step in the reverse engineering process. Producing a useful result requires proper preparation, accurate capture data, and cleanup. Alongside that, you always need good engineering judgment to truly resolve the problem. Thank you for watching, and remember, make your ideas reality.